Electrician Program. This is chapters 13, 14, 15, and 16. Chapters include 13, appliance wiring and special outlets, 14, farm wiring, 15, mobile home wiring, and 16, swimming pool wiring. 13, appliance wiring and special outlets. General considerations. A separate appliance circuit may be designed and connected to supply both 120 and 240 volts for devices such as electric ranges and clothes dryers. These appliances may have different voltages needs at certain times during their operation. For example, clothes dryer circuits are varied and may be split so that high heat is supplied at 240 volts while low heat is supplied at 120 volts. Figure 13-1 is a schematic for such a circuit. With only rare exceptions, the appliance is connected directly to the power panel. It is protected by the branch circuit breaker that also may serve as a disconnecting means. Most hookups are made with a pigtail plug, a short cord and plug combination that is attached to an appliance, and a receptacle. This is a common practice with clothes dryers and electric ranges, see figure 13-2. The pigtail receptacle method involves running the conductors from the service panel to the receptacle. Then, through the use of the pigtail plug, the circuit is completed to the appliance. Still, another method used is the system illustrated in figure 13-3, bottom left. Here, provided the appliances are close to one another, a high amperage appliance power panel is installed. The various appliance circuits are run from this sub-panel at 20 amps each. This works well in kitchens with built-in units or in utility rooms. In general, the hookups for a range is a 3/4 wire pigtail plugged into a 50 amp heavy duty receptacle. The fourth terminal is for the equipment ground. Appliances should be placed on a separate circuit if, as in the case of washers, dryers, ranges, garbage disposals, dishwashers, pumps, motors, and the like, they are rated above 12 amperes or 1/8 horsepower or 240 volts. See figure 13-4. Appliance classification. In Article 550 of the NEC, it separates appliances into three types: fixed, portable, and stationary. Since this article covers mobile homes, these definitions do not apply anywhere else in the NEC, although it may be helpful to read and understand Article 550, refer to Article 422 for most appliance issues. Kitchen appliances. There are two concerns when wiring for kitchen appliances. These units typically have larger amperage requirements, and the appliances may be used with or near water. When installed correctly, these appliances make many kitchen chores easier while maintaining a proper level of safety. Garbage disposal unit. Garbage disposal units, such as the one pictured in 13-5 may be controlled directly from the panel circuit breaker, from a plug and cord connection, or most often with a on and off switch. They are rated at approximately 5 to 10 amps and 120 volts. Since garbage disposals must be or must have an overcurrent protection not exceeding 125% of their motor's full load current rating, a 15 or 20 amp breaker is usually sufficient. Dishwashers. Most dishwashers have a cord and plug that may be connected to one of the 20 amp kitchen appliance receptacles. Like garbage disposal units, they carry a rating within the range of 5 to 10 amps at 120 volts. In fact, if location permits, the dishwasher and garbage disposal unit can be connected in the same kitchen duplex outlet. Refrigerator and freezers. Refrigerators and freezers should have a dedicated receptacles. Both are motor type appliances and, as mentioned earlier, should have overcurrent protection fuses or breakers rated at no more than 125% of their nameplate current. Connection is almost always by cord and plug. If there is a nearby light that is used frequently, add that light to the circuit for the refrigerator or freezer. This way you will be alerted if a tripped breaker before the food warms up and spoils. Cooking tops and wall-mounted cooking units. Counter cooking tops and wall-mounted cooking units are each rated at approximately 7.5 kilowatts or 7.5 kVAs and 122/240 volts. These types of units require special circuits and overcurrent protection in the form of fuses or breakers, usually 30 to 40 amps. They are connected in the same manner as ranges or dryers discussed earlier. Service entrance cable 8 to 10 AWG is often the method of connection, originating from the main panel or sub-panel directly to the unit. In instances where the units are close, it is permitted to connect the pair to a single circuit, providing the overcurrent protection is suitable for the combined load. See figure 13-6. Room air conditioner units. Air conditioners are connected from either 120 or 240 volts and generally are rated between 4 and 10 amperes. For example, a typical air conditioner may be rated at 1.5 kilovolt amps or kVAs, 240 volts times 6.25 amps. This air conditioner could be placed in a 15 amp double pole breaker or plugged into a receptacle like the one shown in figure 13-7. Other air conditioners which operate on 120 volt can be plugged into any regular duplex receptacle outlet. Air conditioners can often be connected to the same circuit as heating units, since they would not be operating at the same time. In these situations, only the larger load is considered, as explained in the section of non-coincident loads from the previous chapter. Miscellaneous special outlet units. There are several other devices that should have dedicated receptacles and circuits. These devices are merely listed since they are connected in a manner similar to large appliance outlets: central heating, cooling system, attic fans, well pumps, sump pumps, and large shop tools. Water heaters. A single family home or small commercial enterprise will usually have a 30, 40, or 50 gallon water heater. Electric water heaters require a separate 240 volt circuit. In most instances, the water heater is connected to a 2-pole 20 amp or 30 amp breaker at the main panel or a nearby sub-panel. A 20 amp circuit should be used for heaters up to 4 kilowatts, 4 kVAs, while a 30 amp circuit is appropriate for those up to about 6 kilowatts or 6 kVAs. These would be wired up or wired with a 12 AWG or 10 AWG conductor respectively. For this, see figure 13-8. This manner of connecting the water heater will provide a 24-hour heating. Water heaters, like most electrical equipment, must be properly grounded. This is accomplished by bonding the water heater unit casing to the equipment grounding conductor of the cable or to the conduit, if supplied in that manner. Additional bonding to the metal cold water supply pipe is recommended. Heaters. A frequent installation or repair performed by electricians involved electric heaters. These heaters are devices containing resistors through which an electric current passes to produce heat. This heat is subsequently given off to the surrounding area by conduction, convection, or radiation. These are the three methods by which heat travels. Conduction is the method by which heat passes through a substance by the contact of its molecules. That is, the heat energy is transferred from point to point within the substance by molecules touching each other. Due to the nature of this type of heat transfer, it takes place almost exclusively in solid substances. See figure 13-9. Convection is the process by which heat is transferred through fluids, liquids, and gases by the movement of masses moving on equal temperatures. Warm fluid masses rise because they are less dense than the surrounding fluid. Cool fluid sinks because they have greater density than their warmer surroundings. See figure 13-10. Radiation is the primary method by which heat is transferred through energy waves. The waves come out from the source in straight lines and move in all directions from the source. It is the method by which the sun energy reaches the earth. See figure 13-11. Heater installation. Typical home heaters are usually built into floors, ceilings, and walls, or are surface mounted. These heaters are almost always automatically controlled by thermostats that are located close to the heating units or built into it. Some are provided with circulating fans to help force the warm air away from the unit while drawing in the cooler air to be warmed. Many heating units are designed to be completely portable so they can be easily relocated. Types of heaters. Some heating units are available in a great variety of shapes and sizes and power ratings. Units may be square, rectangular, or circular. The heater size has traditionally been given in watts or kilowatts of power used. The NEC specifies that heaters have a nameplate that states the size of the heater in either volts and or watts or volts and amperes. These units may range in size from 750 watts or 750 VAs to more than 7,500 watts. Floor heaters and baseboard units are varied. The size and type chosen depends mostly on the room size and comfort needs. For this, see figure 13-12, which illustrates additional types of heater units. Wall units are common. They have ratings in excess of 6 kilowatts or 6 kVAs. They may be flush mounted, recessed, or surface installed. Various styles of wall units are available. They can operate on the radiation principle called radiant heaters, or they can be fan assisted. Control may be wall mounted or integral thermostat. Floor units. Floor heating units are primarily for two types: floor heating cable and floor duct or drop-in units. These units have general ratings of 120 to 240 volts. The floor heating cables require special installation procedures. Consult the NEC for the local inspector and the manufacturer. Floor duct units are simple to install. The procedures should be explained and illustrated by the manufacturer. Heat is moved in these units by natural convection or a fan. Thermostats are generally wall mounted. Baseboard units, perhaps the most common residential and small commercial type heaters, are baseboard units. Again, these operate at 120, 240, or 208 volts and have a load rating ranging from 35 watts or 35 EAs to about 4.5 kilowatts or 4.5 kilo VAs or kVAs, depending on the size and construction. Thermostat control is possible from either a wall mount or integral position on the appliance. Other units, although only a few specific types of heater units are discussed here, there are many other types of heaters available. Heater units. The choice depends on many factors: size of area to be heated, heat loss factors, amount of insulation present, climatic conditions, desired temperature of the area to be heated, style preference. Other types of electric heaters marketed today are heat pumps, electric furnaces, electric fireplaces, ceiling heaters, outdoor roof mount central heating. Heater circuits. A heater circuit is a schematic drawing showing how the heater operates and the proper way to connecting it to the electrical system. Because the variations in types, makes, and models of heaters, it would be impossible to describe all heater circuits possible. However, the common types of heaters available for home or office installation are fairly similar. Figure 13-13 shows the circuitry commonly found in baseboard units. Generally, these may be wired for 120, 208, or 240 volts. Circuits must be properly grounded. Figure 13-14 shows a typical wall or ceiling heater circuit. Note the similarity in circuitry of the two units. The relay in each case is used because of the time delay needed to compensate for the slow moving contact points within the thermostat. Most units have a built-in relay switches, so there is no need for auxiliary wiring. Figure 13-15 shows a wiring schematic for a heater with a fan-assisted circulation. Moving on to the review questions for this chapter 13. List 5 appliances that require special circuits or outlets, and that is clothes dryers, refrigerator, dishwasher, the space heater or air conditioner, air pump, garbage disposal, etc. 2. Name the 3 methods by which heat is transferred from place to place, that is convection, irradiation, and induction. 3. Motor operated appliances such as garbage disposal units should have overcurrent protection in the form of fuses or breakers that will not exceed 125% of their full load rating. Question 4. A counter cooktop units rated at 8 kilovolt amps or kVAs and 120/240 volts should be on a separate circuit having a double pole circuit breaker of 30 or 40 amps. 5. True or false, heaters may be on the same circuit as room air conditioner units. Know the code. This section is to get you familiar with looking for information in the NEC. For this exercise, I've used the NEC from 2002 and 2014. The page numbers and table numbers may be slightly different, but they are largely similar. Question 1, section 4.422.16b2 covers the court application for which two types of appliances, that is built-in dishwashers and trash compactors. Question 2, true or false, is the term counter-mounted cooking unit defined in the NEC? And the answer is yes. You can find it in page 70-29 in the 2014 NEC. What is the voltage? Question 3, what is the voltage limit for room air conditioners covered under section 440.60? Again, 440.60. And that is 250 volt. The answer again is 250 volt, found in page 70-318 on the 2002 NEC. Moving on to chapter 14, farm wiring. Some of the objectives for this chapter are to design and install an electrical power distribution system for a farm, describe an appropriate grounding system, select materials and components for corrosive and damp conditions found on farms, install farm wiring, and finally to compute and design adequate circuits for various farm buildings and operations. Some of the technical terms in this chapter are connected load, demand load, NEMA 4X, and yard pole. The sizes of farms and their production capabilities are increasingly larger and are increasing at a rapid rate. Accordingly, these electrical demands must be met with good quality and high capacity electrical systems. NEC requirements for wiring methods used in agricultural buildings are detailed in Article 547. Again, Article 547. You should be familiar with these requirements before attempting any farm wiring. Farms are complex operations requiring careful planning and layout considerations prior to the actual installation of electrical equipment. A farm should be thought of as a small industrial plant that has several buildings. Operating towards that end, each unit or building requires electrical power. Power distribution. The electrical power is brought to the farm by the power company. The service drop in this case ends not at the dwelling, but rather at a centrally located yard pole. The power is subsequently redistributed from the pole to the individual buildings. The farm buildings may include a dairy or stock barn, equipment shed, hog barn, poultry house, machine shed, granary, a garage, and a farmhouse. Figure 14-1 illustrates electrical power distribution on a typical farm. Farm equipment. As with any electrical installation, the total electrical demand should be calculated before beginning actual wiring. Farmers, by necessity, have great electrical needs, and these must be accurately calculated. For example, devices such as milking machines, coolers, silo unloaders, feed conveyors, barn cleaners, fans, feed mixers, and other motor-driven equipment are typically found on modern farms. Figure 14-2. Each of these devices, as well as many others, must be properly wired and connected for safe and efficient operation. operation. Almost all modern farms require a 200 to 400 amp service entrance. The yard pole service drop. Although each building will have its own service panel containing fuses or breakers for meter for overcurrent protection, the service drop and meter will be located at the yard pole. This will serve as a power center and overall disconnecting means for the farm. The yard pole is shown in figure 13-3. A fire pump disconnect and emergency power transfer switch may also be located here. Grounding. Farm electrical systems often have many grounds. There may be ground rods driven throughout the property to reduce grounding conductor lengths. Buildings with concrete floors may have the electrical system grounded to the reinforcing rods. If copper piping is used for a water supply, the system may be grounded to the water pipe. A reliable grounding system is crucial in farm buildings because of the dampness. For this reason, metallic sheeted cable and metal conduit are not suitable for farm wiring systems. Again, metallic sheeted cable and metal conduit are not suitable for farm wiring systems. Too often, the metal corrodes and weakens the ground, creating a hazardous condition. To ensure proper grounding and safe wiring in farm buildings, metal equipment is used as little as practical. Non-metallic cable, such as NMC and UF, and non-metallic outlet boxes, such as the ones shown in figure 14-4, are preferred. The ground is established through a ground wire within the non-metallic conduit or cable, as shown in Chapter 9, Grounding. This ground wire is made continuous from the ground at the service entrance to all parts of the system. Sometimes additional ground rods are located near and connected to motor-driven devices, such as large fans and conveyors. Metal equipment and structures, such as metal stanchions and floor grating, should be grounded as well. Special devices. On many farms, surface-mounted non-metallic units are used in place of metal outlet boxes. These non-metallic units are preferable in damp locations. These units are self-contained, being combinations of box and switch, box and lamp holder, or box and receptacle. These devices are connected with the NMC, LFMC, or UF cable. Other special devices and equipment used on farms may include vapor-proof light fixtures, timer switches, waterproof or reflector yard lights, lightning arresters, weatherproof or outdoor switches, and outlet boxes. See figure 14-5. Motor disconnects and controllers should be housed in NEMA 4X enclosures, especially in damp, wet areas. NEMA 4X is a standard for electrical enclosures set by the National Electrical Manufacturers Association, or NEMA. When a manufacturer states that an enclosure meets the NEMA 4X standards, the enclosure is designed for outdoor use. Dairy barn. The dairy barn requires the most electrical power of any building in the farm. Indeed, it is the center of the farm. The numerous motor-driven machines must be carefully considered when calculating feeder load requirements. Cable or conduit. Running of cable race or raceways in barns and outbuildings should be done with the same care as residential wiring. Make your parallel runs along the sides rather than the bottoms of beams and joists. Make cross runs through drilled holes rather than over the edges. If runs must be made across the surface, protect the cable with 1x4 boards. Place wiring where it will be protected from weather wherever possible. Electrical outlets should be plentiful. One outlet every 12 foot or closer is best. Receptacles may be located along the walls behind the stanchions. The receptacles should be mounted no lower than 60 foot, or the receptacles should be mounted no lower than 60 inches or 1.5 meters above the floor. Higher is even better as it prevents them from being damaged by animals or tools. Lights should be located both to the front and rear of the stanchions. A 60-watt porcelain or plastic fixture placed every 15 foot or 4.6 meters is sufficient. Dust-proof lights should be installed in the feed storage, silo, and haymow areas. These lights should be controlled by a wall switch at every entrance to the area. Open feeding areas as well as calf pens should be provided with similar outlets and lighting circuits. Locating lights. Place lights at alley crossings, stairs, ladders, chutes in the dairy farm. If ceilings are dark, use reflectors so light is directed downward rather than to the ceiling. Place the lights where joists, beams, and posts will not obstruct the light from a fixture. Place switches so that lighting can be controlled at all entrances to the building. Use three-way switches. As with residential wiring, pilot lights are advisable. When switches control lights that cannot be seen from the switch location. The milk house and milking parlor should have similar lighting and receptacle arrangements as the dairy barn. Again, lighting should be plentiful with outlets mounted high enough to avoid damage. Special branch units or special branch circuits will be required where the facility includes bulk tank storage or motors for running vacuum pumps or milking machines. Poultry house, hog barn, sheep house, and horse barn. These buildings must be well electrified, although the electrical demand for these buildings is much less than that of the dairy barn. Lighting should be plentiful. One light for every 150 foot squared of floor area is suitable. Wall switches or wall switch lights are advisable. Timer switches to increase egg production should be a part of the lighting circuits of the poultry house. Receptacles should be located every 12 to 15 foot along the walls and mounted no lower than 5 foot above the floor. Computing farm requirements. Each building's electrical needs must be computed carefully to determine the total farm load. The farmhouse power requirements are calculated using methods that are the same as any residence. The other buildings, barns, sheds, and shops are computed differently. The farm buildings, having more motors, heating devices, and lighting circuits, will often require more power than the farmhouse. The procedure for computing such demands begins with a list of buildings Include the farmhouse since it will be also connected to the yard pole service drop. The list might appear something like this: a farmhouse, a barn, the equipment or tool shed, poultry house, and a hog barn. Barn electrical requirements. Start with the barn since it probably will have the greatest electrical demand. List the number of lighting circuits, special appliances and motors, and other equipment that it will need. For example, 15 lighting circuits at 120 volts at 15 amp or 20 amps. 6 motors with the following horsepower: half, 1 horsepower, 2 horsepower, and 3 with 4 horsepowers. 1 water heater and 1 sterilizer. Next, determine the volt amperage requirements. A good rule of thumb for general lighting circuits is about 400 VAs each. For motors, see chapters 18, motors. For heaters, sterilizers, and various other pieces of equipment, use nameplate ratings stamped on the equipment housing. Also consult chapter 13, appliance wiring and special outlets, and tables under Article 430 of the NEC. See Figure 14-6. Add up the total power needed by the building. Lighting circuits equals to 6,000 VAs. Motors total times 0.5 equals to 8,600 VAs. Heater is 5,000 VA. Sterilizer 7,000 VA. And the total is 26,600 VAs or 26.6 kVAs. Note the 50% factor may be used when not all motors will be operating at any given time. The same procedures is followed for each of the farm buildings. The home is not included. It must be calculated separately using the requirements covered in Chapter 12, branch circuit feeder and service design. Add up the totals. The figures may look something like this. Farmhouse equals to 25.6 kVAs. Barn equals to 26.6 kVA. Equipment tool shed equals to 7.5 kVA. Poultry house 6.3 kVA. Hog barn 3 kVA. And the total farm power needed is 69 kVA in this case. This total 69 kVA is called the connected load. It represents the amount of power needed if all of the equipment were operating at the same time. Again, the connected load represents the amount of power needed if all of the equipment were operating at the same time. A more conservative figure called the demand load represents the amount of power that would be most probably needed at any given time. Again, a more conservative figure is the demand load, which represents a amount of power that would be probably needed at any given time. Generally, the minimum demand load is considered to be about 35% of the connected load. Based on this figure, the wire sizes and overcurrent protection at the yard pole are determined. Again, based on this figure, this 35% of the connected load, The wire sizes and overcurrent protection at the yard pole are determined. In our example, 69 kVAs times 0.35, which is 69 kVA at 35%, equals to 24.15 kVA, or 24,150 VAs. This at 240 volts, we arrive at 100 amps as our current needed for the farm. Do not forget to consider the future growth, which would demand an increase in power conditions. Thus, the sizes of service conductors should be at least one size larger than the ones calculated. In this case, 4 AWG would be minimum, but a wiser choice would be 2 AWG or 1 AWG. Without a doubt, this would be a very small farm. Use the same method to determine the wire sizes for the feeders interconnecting the various buildings to the yard pole. Figure 14-7 may serve as a general rule or general guide for the average farm structures equipped with typical devices. However, these ratings should be verified when the farm equipment is selected. Moving on to the review questions, which are already answered here. 1. Generally, the farm service drop ends at a centrally located distribution point called the blank, fill in the blank. The answer is yard pole. Fill in the blank again, or answer the question. Question 2, list the 3 common farm buildings other than the farmhouse that require electrical service equipment. Some of them include the poultry house, hog barn, sheep house, and the machine shed. There may be others. Question 3, fill in the blank. Most up-to-date farms require a blank ampere service as a minimum, and that is 200. It can range from 200 to 400 and up. That is in amps, amperage. Question 4, indicate which of the following wiring system is recommended for farm buildings. And the answer is B, non-metallic conduit or PVC. You should avoid all kinds of metallic equipment or conduit. Moving on to the know the code section. Question 1, according to table 220.103, the second largest load will have a demand factor of 75%. That is in page 70-76 of the 2014 NEC. Question 2, the three phases or the three phrases that are defined in Article 547.2 are distribution point, equipotential plane, and site isolating device. These are in page 70-478 of the 2011 NEC. Finally, question 3, Article 547.9D requires the grounding conductor to be 6 AWG minimum or 8 AWG if it's copper. And you can verify this question. The verbatim in the NEC may vary depending on the year that you use. Mobile home wiring. This is chapter 15. Objectives include to demonstrate the familiarity with the NEC requirements for mobile home electric service and wiring, compute loads for mobile home circuits, and to define terms applying specifically to mobile home electrical systems. Some of the technical current terms include distribution panel board, feeder assembly, mobile home service equipment, and mobile home. Article 550 of the NEC applies to all mobile home or to all mobile homes. A mobile home is a residential structure that is transportable in one or more sections and is intended to be used without a permanent foundation. A permanent chassis supports the home before, during, and after installation. The basic electrical service components of a traditional house are adapted to meet the temporary requirements of a mobile home. See Figure 15-1. Distribution panel board. A distribution panel board corresponds to the service electrical panel in a permanent structure. It must be securely fastened to a structural member of the home either directly or by using a substantial brace. See Figure 15-2. The mobile home distribution panel board receives its power supply through the feeder assembly. An electrician will rarely install this distribution panel board since the manufacturer of the mobile home almost always supplies it. The feeder assembly. The feeder assembly includes the conductors with their fittings that carry electrical current from the mobile home service equipment to the distribution panel board inside of the mobile home. See Figure 15-3. The feeder assembly must have 4 conductors. 3 must be insulated circuit conductors, 2 ungrounded and 1 grounded. The 4th is the insulated green grounding conductor, depending primarily on the calculated electrical load of the mobile home and any additional requests of the owner. The electrical feed can be supplied by any of 3 different ways. A mobile home power supply cord. This is permitted if the load is 50 amps or less. However, if the mobile home has factory equipped gas or oil heating and cooking equipment, a 40 amp cord is permitted. Figure 15-4 shows a typical installation. The cord which must always be approved and labeled for mobile home use, must be no shorter than 21 feet and no longer than 36.5 feet from end to end. The plug must be of molded type. The opposite end of the cord must be permanently attached to the distribution panel board in the mobile home. This is Figure 15-4. One common hookup for a 40 or 50 amp mobile home uses the power cord. And one end of the cord is permanently wired to the distribution panel board in the mobile unit. The other end will plug into a 120 to 40 volts with a 50 amp circuit to each. A 20 amp circuit is also available for other purposes protected by GFCI. A clamp should be provided at the panel board knockout to prevent strain on the cord from damaging the cord or its connections to the terminals. See Figure 15-5. Only 1 cord per mobile home unit is permitted. See the NEC section 550.10. An overhead installation consisting of a mast and a weatherhead. This type is for permanent installations or where the load exceeds 50 amps. See Figure 15-6. An underground lateral service using cable or conduit. This is an alternative to an overhead permanent installation. It is the most common method used. See Figure 15-7. The underground lateral service must follow typical depth requirements based on the materials used. See figure 15-8. Mobile home service equipment. Mobile home service equipment is all of the equipment, including the main disconnecting means, overcurrent protection devices, and receptacles or other arrangements for connecting the supply end of a mobile home feeder assembly. The meter may be regarded as a part of the service equipment. Service equipment should not be mounted on the mobile home. The NEC requires that the service equipment must be within sight and located a specific distance from the home, usually 20 or 30 feet away. The equipment must be supported by a pole or pedestal arrangement. Sometimes the main disconnect, breaker, and meter are mounted together. In other cases, the meter is mounted on a pole and the overcurrent protective devices are on a pedestal. Overhead installation. The mast and weatherhead installation must have 4 continuous conductors that are color coded. One of the conductors must be an equipment ground. For this, refer to Article 230 of the NEC. For the proper conductors to be used, see Articles 550.10. The service lateral. For a lateral installation, that means underground, the mobile home must be fitted with a metal or rigid non-metal raceway that connects to the distribution panel inside the unit and extends to the underside of the chassis. The raceway must have a provision for attaching a junction box. The manufacturer may or may not have provided the raceway with the conductors. Refer to NEC section 550.10b. The electric utility company usually installs the necessary service drop and transformer. The customer must supply the service pole and its components, as well as the meter pedestal for underground supply. Both pole and pedestal are permanent installations. The pedestal must be rigidly mounted so that it cannot be easily knocked over. Figure 15-9 illustrates a typical pedestal or pedestal arrangement. Devices and outlets. The various electrical devices and equipment are almost always installed by the manufacturer and must meet minimum NEC requirements. These are checked by the electrician and the electrical inspector for proper polarity and grounding. Distribution panel hookup. The distribution panel, along with a main breaker for branch circuit disconnect purposes, is usually installed by the manufacturer. To connect the power supply feeder assembly to this panel, carefully study figure 15-10. Note particularly that the neutral conductor is completely insulated and isolated from the grounding conductor, as well as the equipment enclosure. Again, the neutral conductor is completely insulated and isolated from the grounding conductor, as well as the equipment enclosure. In addition, the mobile home chassis must be securely bonded to the grounding bus or grounding conductor, as must all metal, non-current carrying equipment inside of the mobile home. This grounding continuity is essential and will be checked by the inspector. Calculating the panel board load. The distribution panel load of the mobile home is computed using methods that are similar to those used for a standard residential load, with some minor differences. Lighting and small appliance requirements are determined similarly to other one or two family residences. The 3 VAs per foot squared, 2 small appliance circuits, and 1 laundry circuit rules are used. Add to this the nameplate ratings for motors and the loads for heater, garbage disposal, dishwasher, water heater, clothes dryer, wall-mounted oven, cooking units, and similar appliances. Freestanding ranges, unlike wall-mounted ovens or cooktops, are rated at 80% of their volt amperage up to 10,000 VAs. Beyond that, figure 8,000 VAs for those loads between 10,000 and 1,200 or 12,500 VAs. Add 400 VA for every 1,000 VA increase above 12,500. The smaller of the heating and cooling loads can be omitted from the load calculation. Here's an example of how to apply these rules for a mobile home. Find the total electrical load for a 65-foot by 12-foot mobile home. It has 2 small appliance circuits, a laundry circuit, a 2500 VA space heater, a 100 VA fan, a 500 VA dishwasher, and 800 VA air conditioner, 8,000 VA range, and a 5 kilo VA or kVA water heater. As you can see, the steps on the screen, find the general lighting and small appliance loads as follows. 1. Find the area. 65 times 12, that's 65 feet times 12, equals 780 square foot. That's the square footage for the home. Step 2, multiply 3 VAs for each square foot, which in this case is 780 times 3, which gives us 2,340 VAs. Add 2 small appliance circuits at 1,500 VAs each, or 3,000 VAs, plus the VAs that we get from the square footage, which is 2,340 VAs, which gives us 5,340 VAs. Step 4, add 1 laundry circuit at 1,500 VAs, which is 1,500 VAs plus the 5,340 VAs, which it gives us 6,840 VAs. Step 5, the first 3,000 VAs is retained at 100%, which we get 3,000 VAs, of course, at 100%, and the remainder is reduced by 35%. So we take 3,000 from 6,840. We are left with 3,840. We have to reduce that by 35%. We multiply it by 0.35, so 3,840 times 0.35 gives us 1,344 VAs. Of course, we have to add that to the 3,000 VAs which we have at 100% in step 7. We get 4,344 VAs. This again is the net lighting and small appliance requirements, 4,344 VAs. Step 8, divide the previous answer by the voltage to get the lighting and small appliance VA, or the small appliance amperage. Again, step 8, divide the previous answer by the voltage to get the lighting and small appliance amperage, which is 4,344 divided by 240 volts gives us 18.10 amps. Step 9, find the amperage for the space heater, which in this case is 2500 VAs divided by 240 volt, which gives us 10.42 amps. Find the amperage for the fan, or 100 VAs divided by 120 volts, or 0.83 amps. 11. Find the amperage for the dishwasher, which is 500 VAs divided by 120 volt, or 4.17 amps. 12. Omit the air conditioner. Only heating or air conditioning is computed, whichever is larger. In this case, step 13, find the amperage for the range, which is 8000 VAs divided by 240 volt, which is 33.3 amps. Step 14, reduce by 80%. So 33 amps times 80 times 0.8, or at 80%, is 26.64 amps. Find the amperage of the water heater, which is in this case 5000 VAs divided by 240 volt, or 20.83 amps. And then finally, step 16, add all the answers for 8, 9, 10, 11, 14, and 15, which are in this case 17.10 amps plus 10.42 amps plus 0.83 amps plus 4.17 amps plus 26.64 amps plus 20.83 amps, which gives us a total of 80.99 amps. So the total is about 81 amps, therefore a 100 amp service is needed. This is considered the minimum for a mobile home. Mobile home parks. The NEC Article 550 outlines the various requirements for mobile home parks. The general demand factors to be considered are shown in figure 15-11. The application of these demand factors may best be illustrated through the use of an example. If a particular mobile home park is to accommodate 25 mobile homes, we would use the demand factor of 24%. This is the minimum. For example, assume that the largest mobile home that will fit in the park has a calculated load following section 550.18 that is less than 1600 VA. Section 550.31 requires you to use at least 1600 VA for each mobile home lot, or 1600 or 16,000 VA times 25 equals 400,000 VA. Again, to repeat, for example, assume that the largest mobile home that will fit in the park has a calculated load following the section 550.18 that is less than 16,000 VA. Section 550.31 requires you to use at least 16,000 VA for each mobile home lot. 16,000 VA times 25 equals 400,000 VA. According to table 550.31, the demand factor for mobile home parks with 22 to 40 lots is 24%. So 400,000 VA times 0.24 is 96,000 VA. The mobile home park will be supplied with a 240 volt service. So 96,000 VA divided by 240 volts equals 400 amps. The mobile home park will need at least 400 amp to supply power to the mobile homes. In addition to this load consideration, the electrical requirements of common park facilities and equipment, such as security lighting, must be added onto the overall service total demand, or the overall total service demand. Refer also to the NEC Article 550.30. That is the example that we just discussed. Moving on to the review questions for this chapter, chapter 15. Number 1, list 2 factors that distinguish mobile homes from ordinary 1 or 2 family residences. 1 is the temporary nature of mobile homes. They are movable in theory. And 2, they have no permanent foundation, at least most of them, or a great number of them. Question 2, where must the service equipment or main disconnect and meter be placed for mobile homes? The answer for this is C, on a pole or pedestal separated from the mobile home. Question 3, mobile home power cords must be no less than 21 feet and no more than 36.5 feet long. Question 4, the grounded neutral conductor must be insulated and isolated from the grounding conductor within the mobile home distribution panel. Question 5, the lighting load of a mobile home is based on 3 volt ampere or 3 VA per foot squared rule. Question 6, the minimum service rating for a 20 unit mobile home park would be 333 amperes. And that is how you go about finding that out. 16,000 VAs times 20, or 320,000 times 0.25 or 25%, which is 80,000. You divide 80,000 by 240 volts, gives you 333 amps. Moving on to the Know the Code section. Number 1, which section of the NEC lists definitions for mobile homes? And that is Article 550, page 70-481 of the 2011 NEC. Question 2, how many requirements for receptacle outlets are listed in Article 550 of the NEC? And as far as I can find, it's 9 of them, page 70-485 of the 2011 NEC. Finally, question 3, which section of the NEC covers wiring methods for mobile homes? And if I understand the question right, this is section 3 of the Article 550 of the NEC, which can be found at page 70-447. This is based on the 2002 NEC. Moving on to the last chapter of this section, swimming pool wiring. Some of the objectives in this chapter are to list in detail the rules for bonding metal fixtures and parts around a swimming pool, explain grounding requirements for swimming pool wiring, give the NEC requirements for wiring underwater light fixtures, name the fixture types used in pools, and cite the NEC rules for overhead conductor clearance around the pool area. Technical terms used are dry niche fixture, forming shell, stray currents, and wet niche fixture. Installation of an electrical wiring in and around swimming pools, indoor and outdoor, is of much concern to the NEC. The requirements for such installations provide rules that will ensure safety. Bonding. The specific installation requirements for swimming pool wiring methods are found in Article 680 of the Code. Due to the presence of water, the possible pathways of electrical currents must be strictly controlled. Any stray currents, those currents that do not follow the intended path, moving between metal parts in and around the pool can be extremely dangerous. These stray currents must be kept at earth potential, which is zero. The bonding of all metal parts accomplishes this and is therefore essential. See figure 16-1. Specifically, the following must be bonded using a 8 AWG solid copper conductor. Metal parts with 5 foot horizontally, within 5 foot horizontally of the pool walls, including fencing, awnings, door and window frames. Metal parts within the pool walls, including the shells for wet niche fixtures. And metal parts of the pool structure, including the reinforcing steel, steel decking, ladders, and diving board supports. Also, accessory equipment including pump motors, fittings, conduits, piping, and skimmer components. The only job of the bonding conductor is to interconnect the metal parts. This conductor can be bare or insulated. It may be run on a panel board or service panel ground block, but this is only required if that equipment is within the parameters specified above. Grounding. In addition to bonding, all electrical equipment related to the pool and within 5 feet of the interior walls must be properly grounded. This creates a low resistance pathway for fault currents or fault related current to get back to the neutral so that fuses or circuit breakers will operate correctly. The grounding conductor must be properly sized for the particular circuit as listed in NEC table 250.122. It cannot be smaller than 12 AWG copper. Also, the grounding conductor must be insulated and run in conduit with the circuit conductors all the way back to the supply panel ground or the supply panel grounding terminal block. Figure 16-2 shows the correct way to ground electrical equipment in and around the swimming pool. Receptacles. The only receptacle permitted by the NEC to be located within 10 foot of a pool wall is a receptacle for a cord connected swimming pool pump. The pool pump receptacle must not be any closer than 5 foot from the pool wall. Further, the NEC requires that a minimum of one 120 volt GFCI protected receptacle be located between 10 foot and 20 foot of the pool wall for use of cord connected devices. This requirement is intended to eliminate the possible use of extension cords originating from inside of the home, and any additional outdoor receptacles within 20 foot of the pool wall must also be GFCI protected. Of course, all receptacles installed outdoors for residential buildings must have GFCI protection. Figure 16-3 shows basic rules and requirements associated with receptacles around the pool. Switches. All switches or switching devices of any type must be set back 5 feet, must be set back at least 5 feet from the pool edge. If not, there must be some type of fixed permanent wall or barrier between it and the pool. Lighting. Pool lighting may be viewed as falling into one of 3 categories for all practical purposes. Lighting that is that existed around the pool area prior to the pool installation, which will remain after the installation. Newly installed lighting is associated with the pool area. And lighting which is installed within the pool structure itself. Looking at each of these categories will provide a general scope of the installation methods. The NEC allows existing lighting fixtures to remain as they are, even if the fixtures fall within the otherwise prohibited 5-foot perimeter of the pool side. This is allowed only if the fixtures are rigidly attached to a structure and GFCI protected. Remember, however, that switching of the lights must be located at a point beyond the 5-foot area. This important safety factor should not be overlooked. The new lighting fixtures may be installed not less than 5 foot horizontally from the pool edge and will require GFCI protection. Lights may also be installed above the pool and should be no less than 12 foot above the water line for outdoor pools, or no less than 7 foot 6 inches above the water line. For indoor pools, indoor lights again, lights may also be installed above the pool and should not be installed less than 12 foot above the water line for outdoor pools and no less than 7 foot 6 inches above the water line for indoor pools. Indoor lights and fans above the pool must be GFCI protected and totally enclosed. The basic requirements for pool side and above pool lighting are illustrated in figure 16-4. Refer to sections 680.8 and 680.22. Underwater lighting. The installation of underwater lighting fixtures is a subject requiring careful attention. Due to their location, these fixtures can initiate severe electric shock if not installed properly. For this reason, grounding, bonding, and sealing requirements must be strictly followed. Additional requirements include the following. Only UL or other lab tested and listed lighting fixtures are to be installed. Fixtures may not exceed 150 volts between their conductors. Fixtures that operate above 15 volts must be GFCI protected. When installed, the fixture's top edge must not be, or when installed, the fixture's top edge must be at least 18 inches below the normal water level. Note that certain fixtures may be installed at a minimum of 4 inches below the normal water level, only if identified for that use. If the fixture shall have some inherent means to protect it against overheating. Raceway between the fixture and the junction box or transformer for low voltage fixtures must be either rigid or intermediate metal conduit made from brass or other approved corrosion resistant metal, liquid tight flexible non-metallic conduit, rigid non-metallic conduit having an 8 AWG insulated copper conductor to connect between the fixture and the junction box or transformer enclosure. Wet niche fixture. The wet niche fixture is made up of a lamp within a housing, a flexible cord, and a sealed lens. The fixture assembly is enclosed in a metal shell called a forming shell, which is built into the pool wall. The flexible cord is long enough to allow the fixture, when removed from servicing, to extend out onto the pool deck. The wet niche fixtures are usually rated at several hundred watts with 12 volts of electricity from a weatherproof enclosed transformer. This transformer must be located at least 4 feet from the pool edge and elevated at 5 inches above the pool deck or ground adjacent to the pool. A flush deck box mounted at 4 foot from the pool edge is permitted if the box is fully sealed with potting compound and only if the fixture is rated at 15 volts or less. Figure 16-5 shows many of the main points concerning the wet niche fixtures and various wiring methods. Dry niche fixture. The dry niche fixture is an underwater pool light that is installed inside a watertight enclosure within the pool wall. This type has a drainage pipe provided so that any moisture will be removed. A deck box is required and must be installed flush with the deck surface at a minimum of 4 foot from the pool edge. This deck box is where the dry niche fixture is connected to the electrical supply. The dry niche fixture is illustrated in figure 16-6. Notice the cord and the plug connection and large deck box for maintenance, repair, and relamping. Miscellaneous equipment. Often pools are equipped with accessories such as heaters, skimmers, audio systems, and automatic pool covers. Manufacturers provide important installation instructions and information that must be understood to ensure a safe environment. As with all electrical items to be wired within or around a swimming pool, care should be taken to ensure proper grounding and bonding as a number one priority. Refer to Article 680 of the NEC and consult with the local electrical inspector when questions arise. Overhead conductor clearance. It should be emphasized that conductors should not be run above a swimming pool. However, for utility company wiring, there are some exceptions worth noting. Keep in mind that these exceptions are only for service lines such as telephones, television, or power cables provided by the utility. Further, even within the allowable exception criteria, the conductors must not pass directly over the pool or within 10 foot horizontally from the inside edge of the pool. Figure 16-7 shows what is permitted according to the section 680.8 and table 680.8 of the NEC. Moving on to the review questions for this chapter. The number 1, the two basic types of pool lighting fixtures are wet niche and dry niche. Number 2, all metal structures in and around the pool must be bonded. Number 3, the raceway between a fixture and a junction box or transformer for low voltage fixtures must be rigid IMC or intermediate metal conduit or other approved corrosion resistant metal conduit. Number 4, except for the pool pump receptacle, all receptacles around the pool area must be at least 10 foot from the pool walls, and they also must be GFCI type. Number 5, a grounding conductor to pool electrical equipment devices must never be smaller than a number 12 AWG copper. Moving on to the Know the Code section. Number 1, which part of the forming shell is covered in section 680.23b2, and that is wiring extending directly to the forming shell. 2, name the section that regulates the motors of electrically operated pool covers, and that is section 680.27b, found in page 70-532 of the 2002 NEC. Finally, question 3, the figure in the NEC that illustrates clearances from pool structures is 680.8, found in page 70-525 of the 2002 NEC. And this concludes chapters 13, 14, 15, and 16 of the Electrician Program. Congratulations. Please move on to the next chapter after all of the review questions and know the code questions are completed. Thank you.